Hello, we have another piece of vintage test equipment for repair. This time it is Fluke 341A DC voltage calibrator. It is a precision 6-digit voltage source with 3 ranges 10, 100 and 1000 volts. I picked it up on eBay. It was described as used, powering up and producing some output. Apparently they thought so because the meter on the front panel showed some voltage. The price was reasonable, so I bought it, and unfortunately it was slightly damaged in transit because of a combination of two things. On the one hand, the seller was not very careful packaging the thing. It was loosely put in a box with some packaging material around it, but it was not attached properly with the tape to the unit, so the unit was able to slide around in the box. And on the other hand, the carrier was not very careful with the box. So as the result, this handle on the right side broke off, as well as this tilting bail on the bottom. Here are the plastic pieces which held the tilting bail, and one of them completely disintegrated. As you can probably see, I already removed the screws holding the top cover, because I wanted to have a look at the extent of the damage before I make a decision whether to keep the unit or not. And I also wanted to find the bolt which snapped on this side. As you can see, on one side of the handle a small piece of it broke off and it is still attached. On the other side though, the bolt snapped and it fell inside of the unit, so I wanted to find it to make sure it didn't short anything. So I decided to keep the unit, and I negotiated some discount because of this damage. I think I can repair these mechanical problems. I will need to straighten out the front panel a little bit, and I think I can fix this handle. As you can see, the holes are deep and there is enough thread, I think, to have longer bolts. I can glue back this small piece which broke off just for the looks, and then rely on longer bolts to hold the handle in place. But let's worry about mechanical parts after we repair the electronics. Here is one of the pictures of the unit from the auction, and as you can see, the handle was intact, the tilting bail was in place, and it was set to 0 volts, but the meter showed slightly more than 10 volts output. But the links between the output terminals and sense terminals were not installed, so I'm not sure if they tested the thing properly. Let's find out. So here I installed the links between the output and sense terminals and powered the thing up. It is still set to 0 volts, but look at the meter. It goes up and down. Something is wrong with this unit. And look at this, it goes out of scale, something clicks inside and it goes back. I played with it for a while and suddenly it started working. Well, almost. You see, there is some offset around 0.8, 0.9 millivolts, and it's jumping around quite a bit. In this 10 volt range, the offset means 8 or 9 counts here in this decimal place, and there is no way it could be this far off if it worked properly. At most it could be 1 or 2 counts off in the last decimal place. If we forget about the offset for a moment, look, 1 volt, 2, 3, 4, 5, 6, 7, 8, 9 and 10. No problem here. Hundreds of millivolts. No problem here as well. Tens of millivolts. Single millivolts. No problem here as well. And even here we see that it steps by 100 microvolts. No problem at all. And this should be down to the noise, so we could hardly see if it's right or not. And there is another minor problem. We are in the 10 volt range now and the decimal point is here, but if I switch to 100 volts the decimal point should move here and this indicator doesn't light up. And in the 1000 volt range we should see this one and it also doesn't work. But these 5 indicators are lamps, not LEDs, because this thing is so old. So just these 2 lamps are burnt, and probably this one as well, because when I try to limit the current it doesn't light up at all. So I think I need to replace these lamps with LEDs. And let's try the other ranges. 100 volt range, so the decimal point should be here. So this is 10 volts, 20, 30, 40, 50 and so on. Looks like no problem at all, 100 volts. And this is 1000 volt range, so the decimal point is here. So this should be 100 volts, 200 and so on. No problem at all. I have this service manual with full schematics and description of the principles of operation and such. And look at this, John Fluke, June 1969. This company has been around for a while. Look at these specs here. 0.005% accuracy on all ranges. Not bad at all for 1969 and for my $100 if I manage to repair the thing. And by the way, the higher model, which is 343A, has 7-digit setting and accuracy is 20 ppm on all ranges. Not bad at all. Here we have the performance test section in the service manual. The first test here is line regulation. We are supposed to use an autotransformer to vary the line voltage from 115 volts to 126.5 volts. And we should verify that the output stays within 30 microvolts. I don't have an auto transformer, and this test doesn't make much sense anyway at this point, because as you have seen, the output voltage is jumping around in the order of hundreds of microvolts. The next test, which is load regulation, doesn't make sense for the same reason, but the next one after that is ripple, and it makes perfect sense. We should verify that for this model the output ripple is below 100 microvolts RMS or 1 millivolt peak to peak, and we should do that with positive output connected to chassis ground. Also, using some sort of preamplifier is suggested here. Here is the list of recommended equipment, and this preamplifier is not specified at all, except the gain of 1000 and frequencies from 5 Hz to 100 kHz. I don't have anything like this handy. I imagine it should be a precision preamplifier with low noise, low distortions, and precision gain. Let's see what we can do without it. So I moved the grounding link to the positive terminal here. We are supposed to set 10 volts, and I switched the meter into volts AC, and we are reading around 30 microvolts RMS, which is well within specs. So the output ripple doesn't seem to be a problem. And measuring peak to peak with the scope, at least with my scope, seems to be hopeless. Look at this, with nothing connected, and it is set to 1 millivolt per division and AC coupling, we are reading about 1 millivolt peak to peak and about 500 microvolts RMS. We can try limiting the bandwidth to 20 megahertz. This should help a little. Now we are reading about 480, well, about 500 microvolts peak to peak and slightly more than 400 microvolts RMS. This is a bit better, but still not enough. This is why a preamplifier is recommended in the service manual, and that preamplifier must have much better noise floor than this. This thing started misbehaving again, going negative, then going off scale, and then going negative again, and so on. Finally, let's have a look inside. The precision switches are under this cover, so let's take it off. Here we are, and these switches are gold plated and they look perfectly fine, but this section here looks a bit rusty and perhaps needs some cleaning. And here is the bottom of the unit. This happens to be a single board, not two boards as it looked from the top. Revision H. Is this a date code here? 7803 and 7738 on this one in the center. and 7803 on this one. $77.40. This is the oldest one I see so far, $75.21. Let's look what's under this cover. Removed the bolts, and here we are. Not shielded, by the way, just a piece of plastic. I would imagine a couple of reasons for this. One is to keep the dust away from the sensitive part of the circuit, and another is to keep the circuit at the same temperature as much as possible. So, let's clean these rusty switches. Let's use this super contact cleaner with lubricant, perfect stuff for the job. We should apply a small amount right on the contacts and then switch them back and forth a few times. And the other section as well. And now the second switch. This switch has only 3 positions. This is a range switch. And the second section of it Alright, should be good enough. The next thing to do, I think, is to check electrolytic capacitors. Let's grab this LCR meter and start with these big ones. The only way to reach the pins of these big caps is from the bottom, and look at this arrangement. Each cap has 5 pins, and these 4 pins are connected together. I'm going to use these multimeter leads instead of the proper leads for this LCR meter, because I need sharp ends to penetrate the coating on the board. Let's go. The default is 1 kHz, but for larger caps it's better to switch to 100 Hz. And the second parameter, let's set to ESR. So this cap is C1 and it should be 80 microfarads. Here we are, 87, and the ESR is 1.6. And this cap is C2, and it is the same, 80 microfarads. 91, and the ESR is 1.3. Not bad at all, not a problem. I checked all of these big caps and they all look fine. I also checked these 5 blue caps in this section, and they also look fine. For example, this one is C22 and it should be 250 microfarads. We are reading 242 and the ESR is 0.3 ohms. I checked capacitors in this section and I think I found a few problems. First is these 4 capacitors are of the same type, 10 microfarads, 50 volts, and the one I'm measuring now looks fine, 10.5 microfarads, 15.5 ohms ESR at 100 Hz. But let's check another one. Ten microfarads, but almost 30 ohms ESR. And the one next to it, even worse, 50 ohms ESR. And another one, even worse than that, 9.5 microfarads, 83 ohms ESR. So I think they are on the way out. The next problem. These 2 caps are 100 microfarads, 3 volts. And let's check this one. 135, 1 ohm ESR, not a problem. But this second one, 4 microfarads, 170 almost ohms ESR. So this one is completely dead. The next problem. These 2 caps are 5 microfarads, 25 volts. Let's check this one. Well, 5.4, let's say, microfarads, 14.5 ohms ESR at 100 Hz. And the other one, 5 microfarads, but 32, almost 33 ohms ESR. So, clearly it's not as good as it should be. And there is one more cap of the same type here, probably not visible on camera right now. And the ESR is not very good as well, somewhere in between those 2 we measured before. And there is one more problem here. These 2 caps, they are not electrolytic caps. I checked them anyway, and I'm glad I did. They are 0.015 microfarads, or 15 nanofarads. And let's check this one. 15 nanofarads. I'm at 1 kilohertz now. And let's check the other one. It is negative. Why it is negative? Because if we switch to resistance, it's a short. And here they are, C11 and C10. As you can see, this circuit is completely symmetrical. And I checked these diodes and transistors around them. They look fine, no shorts at all. So there is no reason these caps should measure differently at all. I went to a local electronics store and picked up some caps. And because they are cheap, I picked up more than enough of different types, so I can choose. And probably it's a good idea to replace all the electrolytic caps here, but for now let's just try to replace the ones which are clearly bad, and let's see what happens. I desoldered this C11 cap, and sure enough, it is shorted. So these are 0.015 microfarads or 15 nanofarads, 100 volts, 2%. And 2% means within this range from 14.7 to 15.3. I didn't find 2% caps. I picked up 3 different types. These are 5%, 400 volts, and almost all of them are within this range, but they are quite inconsistent all over the range. These are 10% caps, 200 volts, but they are very consistent. All 4 are very close to 14.8. There we go, 14.869. And I don't know tolerance for these guys. They are also very consistent. They are 100 volt caps, and all of them are close to 15.1, 15.17, and this one is 15.10. So I'm thinking about using a couple of these or a couple of these, and it's obviously better to replace both so they are close to each other and have the same temperature drift and such. I don't have unfortunately full specs for any of those caps. Instead of these 10 microfarad 25 volt caps, I picked up these guys, 10 microfarad 63 volt caps, and the ESR is about 10 ohms. This is at 100 hertz. This one, 100 microfarads, 3 volts, by Sprague, we found to be completely dead. So I picked up a couple of Nichicon 100 microfarads, 25 volts, to replace it, and the other one, which looks okay, but I would rather replace both just in case. And these are 5 microfarads 25 volt caps by Sprague, which had a high ESR, so I picked up 6.8 microfarads 63 volt capacitors, also by Sprague, to replace them. There is no 5 microfarad value nowadays, only 4.7 or 6.8. And look at this, 5 ohms ESR, and this is at 100 hertz again. So I replaced some capacitors here, these two 0.015 microfarad ones, these 4 10 microfarad ones, these 200 microfarad ones, and these 3 5 microfarad capacitors, which I replaced with 6.8 microfarad ones. Maybe later I will replace all the electrolytics, but for now let's leave them alone and let's test the unit. Look at this. We are at 0 volts setting, and before we had about 0.8 or even 0.9 millivolts offset here. It's completely gone now. Now the offset is negative 1 or 2 microvolts, which is perfect. Here I have this table in the service manual, output voltage requirements, and there are 2 columns. One is for an instrument that has just been calibrated, and column 2 is tolerances according to specifications. So in this 10 volt range at 0 setting we should be within plus minus 10 microvolts, and we are within plus minus well, up to 3 microvolts, which is well within the tolerance even for freshly calibrated instrument. Let's check 100 and 1000 volt ranges. At 0 settings we should be within plus minus 20 microvolts, and plus minus 60 microvolts. 100-volt range, minus 10 microvolts, well within the tolerance. And 1000 volts, minus 2 or 3 microvolts. Perfect. Let's move on. Next step is 10 volt range, 10 volt setting. We should be within plus minus 200 microvolts in the column 1 or plus minus 1 millivolt in the column 2. So 10 volt range, 10 volt setting, 300 microvolts out, which is slightly out of the column 1 but well within column 2. Next here is 10 volt range, 5 volt setting. We should be within plus minus 200 microvolts or 500 microvolts here. (200 microvolts out), which is right on the edge of the column 1. Next is 100 volt range, 100 volt setting, and we should be within plus minus 2 millivolts in column 1 or 10 millivolts column 2. Let's see. 100 volt range, 100 volt setting, spot on. Next is 100 volt range, 50 volt setting, plus minus 2 millivolts or 5 millivolts in the column 2. Let's see. 1 millivolt out. Perfect. Next, 100 volt range, 10 volt setting, plus minus 500 microvolts column 1, 1 millivolt column 2. Here we are, 100 microvolts, well within column 1. Next, 100 volt range, 5 volt setting, plus minus 300 microvolts or 500 microvolts. So 0 here, 5 here. We are 500 microvolts out, which is right on the edge of the column 2. Next, 1000 volt range, 1000 volt setting. We should be within 20 millivolts column 1 or 100 millivolts column 2. (1000 volt range, 1000 volt setting, and we are 30 or 20 millivolts out, which is right on the edge or slightly out of the column 1 but well within column 2. Next, 1000 volt range, 500 volt setting, plus minus 20 millivolts again or 50 millivolts column 2. 500, and it's perfect. Next, 1000 volt range, 100 volt setting, plus minus 5 millivolts or 10 millivolts. And it's perfect. And the last one, and I believe there's a typo, it should be 1000 volt range because of the decimal point. If it was 100 volt range, decimal point should be in different place. So 1000 volt range, 50 volt setting should be plus minus 3 millivolts column 1 or 5 millivolts column 2. So 50 volt setting, and we are 5 millivolts out, which is right on the edge of column 2. So if we trust my meter, this unit is well within specs, and unfortunately I don't have a better meter. Ideally, a meter should be much more accurate than the unit we are checking. These are comparable in accuracy, which is not ideal, but that's the best I can do at the moment. I took the front panel off to straighten it out and fix the handle. I also need to replace these lamps with LEDs. Alright, I think I managed to get it into a good enough shape. And I also managed to get this piece of broken bolt out. Alright, the handle is in place. That broken off piece I glued with a drop of super glue, as I said, just for the looks, and then slightly longer bolts hold the handle securely in place, no problem. So these lamps are just sitting in short pieces of flexible tubes and shining into these diffusers. Connectors are used on the pins, so they are really easy to replace. And the LED is almost perfect there, slightly loose, so I might need to put a drop of glue or something to hold it in place. And I also need to add current limiting resistors. These are 28 volt lamps. I installed 5 white LEDs instead of the lamps. These are decimal points, and as you can see, this one is shining and the diffuser is yellow. I salvaged these guys from some sort of a flashlight. They work great here. I applied a drop of glue on them to keep them from falling out. And I added 3.3K resistors to limit the current at about 8 milliamps. Look at this. I borrowed this meter 34461A from a friend of mine. It is still branded Agilent with a Keysight sticker on it. Technically it's about the same accuracy as my meter, but it's a new model. And look at this. Certificate of calibration dated 28th of August 2014. So it was calibrated by Keysight slightly more than a year ago, and this, folks, is as good as it gets. I warmed up the equipment for more than half an hour, and we are at 0 setting, 10 volt range, and we are reading about -5 microvolts, which is well within spec for the Fluke. And look how these meters agree almost perfectly, within 1 microvolt. So let's try adding 10 microvolts, which should bring us to +5, which it did. 20 microvolts, 50, and we still see this 5 microvolt offset, 90, still about 5 microvolts down. Let's try 100 microvolts. 400, 800, still about 5 microvolts down. 1 millivolt, 3 millivolts, 5, perfect, 8, 10 millivolts, 50 millivolts, 90, 100, 400, 900, perfect, 1 volt, 2, 5, 10. Meters agree almost perfectly. Let's go to 100 volt range. 10 volts, 20 volts, 90 volts, 100 volts, 1000 volt range. 100 volts, 300, 700, 1000. So this is 10 volts, and if we add 1 millivolt, 2 millivolts, this is all perfect, and meters agree very well. I am very happy with all this. I managed to glue back together this foot with super glue. It was broken into several pieces, and I filled this missing piece of plastic with epoxy. And these feet are supposed to sit on the surface like this. And the second foot has this part broken off partially. So I cut in half a rubber foot like this and added here, and I will cut this one as well and add to this one. And I have more of different sizes, which I think I will add to the back of the unit instead of the missing rear feet. It had only 2 feet on the front for the tilting bale. Here are the front feet installed, and the rear ones as well. I hope you enjoyed this look at such a fine instrument by John Fluke Manufacturing Company. Isn't this amazing? The unit was built in late 70s, so it's about 37 years old, but after replacing a few failed capacitors, it is completely in spec. I didn't have to touch any adjustments. And for the most part, it met requirements for freshly calibrated instruments. Unfortunately, I only had 6.5 digit meters to check the calibration, but the meters agreed so closely that I'm quite confident that everything is great. Thank you very much for watching. If you liked the video, give it thumbs up and subscribe to the channel. Bye!